All right, everybody, it's about 4 o'clock. I think I'm gonna go ahead and get started. Wow, a long time no see. It was March, wasn't it? Since I saw you, and now we're halfway through April. What's going on here? Yeah, so I hope that you guys all had a good spring break, and also thank you for your patience with me last week. I think I told you my parents are getting up there. They're gonna have to get rid of that. They have a 3-story house, just the two of them living in this place. And I'm like, at some point, they're gonna have to like move out. I just hope it's not in the middle of the semester. But anyway, we had a little emergency. Everything's fine now. But I had to go spend a little extra time than I didn't anticipate with them. And I appreciate you guys rolling with the punches, reading your emails, coming into Zoom to watch class and so on. I hope it went okay for you, as best as possible. Obviously, it's not ideal, but we made it work, right? It wasn't so terrible. And now I should be back for the rest of the semester. Unfortunately, on my trip home over the weekend, I must have, the person next to me on the plane, I think must have been ill or something, because I got this bug from them, I think. I don't know who I got it from. But anyway, so I'm struggling a little bit, so I got my mask on here. I am going to have my office hours after my class tonight, but if you wait till 11 o'clock to come in to talk to me at the end of my office hours, if I'm still awake, I might not be making a whole lot of sense. So if you do want to talk to me today, try to catch me earlier than later about anything. We do have a homework assignment due tonight, which is, I think, number 19. Homework 19 is due tonight. And I don't see any questions on the sideboard over here yet, but I will give you a chance to ask some questions, of course, as we go along. Because yeah, there's definitely several problems there that I could imagine people might want to ask me about. So anyway, I'll give you a chance to ask some questions about that. And then as far as for this week, it's gonna be a rough week for me. I have a feeling I'm just kind of starting into this whole thing, so it could be a little rough on Thursday too. But there is an assignment on Friday. That assignment is very short. It's just one section, and it's section 8.2, which every semester I teach this class. Usually people go through that one pretty easily. So we're going to cover that today, and then you'll have till Friday to get that one done. Other than that, we're kind of just on a normal routine here. I did decide to go back. We started chapter 8 in Zoom last Thursday. But as you can see from what's on my board here, I decided to go back. I want to do a little more loose ends and kind of just really solidify the end of chapter 7 one more time. So since we didn't get to do this in person, I thought, well, that should be maybe a good way to start today. So we'll spend roughly the first half of today's class kind of wrapping up some loose ends from the end of chapter 7, and then I will spend the second part of our class going back to chapter 8 again. And in the meantime, we have homework from both 7.3 and 8.1 for tonight. So does that game plan all sound good? So far, so good. Okay, great. One other thing I wanted to mention, we're still 3 weeks out from our next midterm. At some point, I'm going to do the same thing I did for the first 2 midterms, which is there's going to be some extra credit opportunities in the form of a quiz, which will come much later. In terms of videos, because I usually ask you to watch a video as well, but I'm doing so well with being up to par with everything that there may not be a lot of videos. So I am going to give you a slightly different extra credit opportunity this time, or at least part of an extra credit opportunity. But this is going to require your collective effort. So it's a little different than just you doing something individually. And that is that I really appreciate getting feedback from my students about my teaching. I like to know, what did you like? What did you not like? Are there things I could improve, or things that I maybe tried to do that you thought was good or not good or whatever? I just like to hear your feedback on the class, because chances are I'm going to be teaching this again many more times probably. So if there's things I could do better, I'd like to hear about that. Or if there's things that you like that are going on in the class, you want me to keep doing them, Should write those down and tell me to keep doing them. So I really would appreciate if you guys would fill out an SOQ form for me. You could probably already gotten notified about this. If you could fill out one of those for this class, I think you have until May 2nd. So it's not like you have to do it immediately. There's 3 weeks or so to get that done. But what I'm going to do is give everybody 2 extra credit points for the next midterm, provided that I get a response rate. Now, I don't get to read these forms until after the semester is over, but I can see how many people have filled them out. Like I will have an idea what the response rate is, provided that I get a response rate. It has to be better than 85% response rate. Okay. Now, I'll tell you right now, I did this opportunity last semester and they didn't get it. They didn't get it. The reason being that, okay, a couple people have probably drifted away and they're not in the, I mean, they might still be on the roster, but they might not be filling out the form because they're not in the class anymore. So to get an 85% response rate means everybody who's here and still actively engaged in the class really needs to fill one out. If people who are actually here are not filling it out, then we're gonna have a hard time getting 85%. So I would like everybody sometime between now and May 2nd, and I will remind you about this, to fill out one of these forms. And if we reach 85%, everyone will get these extra credit points. Otherwise, no one will get them. So it's all or nothing, and it's kind of a collective effort sort of thing. But yeah, I would really appreciate it if you guys could do that for me by May 2nd. Okay, great. Yeah, I'd like to know, for example, like last semester, I was using my laptop to record the lectures. And it turns out my laptop had terrible resolution. I didn't realize that I was doing these Zoom recordings and then throwing them into YouTube, and people were having a hard time reading them. So I decided this semester I'll try it with my phone. So if you watch some of my Zoom recordings and you have a feedback for me about it, something I could do better with that or whatever, or do you think it's good enough as is? I'd love to know stuff like that. Okay, so anyway, I really appreciate that. Okay, other than that, I don't have any other announcements. Anybody have any questions, concerns, comments?
Come back.
Thanks, it's good to be here. It's so much easier to do this in person. That is for sure. Yeah, so let's just kind of review, because it's been 5 days and we did it in Zoom. So I just want to review this idea of diagonalization again. One more time, like, why do we care about it? How does it work? When does it work? All these kind of things makes a reasonable thing to review. So we take our square matrix A, and we want to know when is it diagonalizable. Remember, that's the same thing as non-defective. The 2 words are synonyms. They mean exactly the same thing. And so what I tried to do here is give you kind of some different ways of looking at it. And I just want to put a box here, right? So in the first place, it just means that every eigenvalue of the matrix should pull its weight. That's the way you hear me talk about it. I like to say it that way. And what does that actually mean? It just means that every eigenvalue creates an eigenspace. This is what E sub lambda is. And the dimension of that eigenspace needs to match the multiplicity of lambda. The multiplicity is just the weight. How many times did lambda show up as a root of that characteristic equation where we solve for the lambdas, right? So when you solve for the lambdas, sometimes the lambdas might repeat themselves. If that happens, I want to know how many times did that lambda repeat itself, and did the eigenspace have exactly the same number of eigenvectors? That's the key equation here. Okay, so that's what it means for the eigenvalue to pull its weight, right? And then more recently, I talked about this on on the perspective of diagonalization, which is that, yeah, if the matrix is diagonalizable, then we can find invertible matrices S and diagonal matrices D such that S inverse times A times S is equal to D. And we talked last week about how to make S and to make B. The columns of S are just the eigenvectors. So we take all of our eigenpairs the lambdas and the V's that go together, and we build S column by column out of those eigenvectors. And we build the eigenvalues down the diagonal of the matrix D with zeros everywhere else. And they just have to be aligned. So if the person next to you puts these columns in a different order, that's fine, but then they have to switch the lambdas into the compatible order as well. So there can be more than one, organization of these columns and diagonal entries, but you got to make them compatible. Right, so as long as you do that, then this equation, S inverse times A times S, will in fact be equal to D. And you might be saying, well, so what? All right, so you find S and you find D and you have this equation. What's so great about it? I tried to show you last week that it sometimes can be helpful for simplifying computations involving the matrix A. I can essentially replace A with D in those computations. Taking powers, for example, of a diagonal matrix, much easier than trying to take powers of the original matrix A. And by powers, I mean matrix multiplication. Take the matrix times itself, times itself, times itself, again and again and again. That's hard to do, right? But if it's a diagonal matrix that you're doing that with, it's a lot easier. So I reviewed that a little bit. I showed an example of that, I think, last week. Also, I have a little video that goes with this Friday's homework that I'm gonna have you watch. It's not very long, but you'll see it on homework 20, which talks about Markov processes, which is very closely related to statistics. And it's a nice application also of diagonalization. So I'll let you watch that video as kind of an extra sort of thing on the side. And just take some notes on it. We're not going to cover it, like I'm not going to put it on a test or anything, but it's a nice video to just kind of get a little bit of an application of diagonalization here. So are there any questions about anything I've kind of summarized so far here? All that stuff in that box? So far, so good? Okay, well, let's do a warm-up problem. This is a typical question. You'll see this kind of thing on the next exam, I'm sure. I'll give you a matrix and I'll just ask you, is it diagonalizable or not? And if it is, let's do the thing where we find S and we find B, which is similar to what the 7.3 homework problems look like. Okay, so I just wanted to do one more example. And here's my matrix A. It's a 3x3. And I'll let you copy that down. And we're going to go through the usual process of finding the first thing we do is we find the eigenvalues and eigenvectors. And then we'll ask ourselves whether all of those eigenvalues are pulling their weight or not. Okay, so let's do that. So for this solution, I'll start solving right here. And we have that matrix A that you see on the left side of that board. And the first step is to get the eigenvalues, the lambda values. And to do that, I have to take the determinant of the matrix that I get when I subtract lambda off of the main diagonal. So let's go ahead and do that here. Just subtract lambda only from the diagonal values. Everything else just stays literally the same. And so this is what we end up with. Any suggestions for how to evaluate that determinant? Yeah, let's expand on a row or a column. Which row or column? Row 3, right? The third row is the one that has those zeros in it. I would probably try to do row 3. So let's just do that. I'm going to expand on row 3 right here. Okay, so let's see if we can make that work. If I expand row 3, 2/3 of my calculation is just 0. Okay, so 0 here, 0 here. The only thing we have to keep track of is the 3 minus lambda entry. And we cross off that row and column and take the determinant of the 2x2 submatrix. This is called the minor, the M33 minor. And so this is using the formula for the determinant of a 2x2. We can quickly write this down. -1 minus lambda times -9 minus lambda, and then with a plus 20 on the end of it. Okay. Now, we don't want to multiply this out. If we were to FOIL it all out right now, we would end up getting a cubic equation. And cubic equations are not always easy to solve for the roots. So I would rather keep it as factored as I can by leaving this 3 minus lambda outside. But inside of these brackets, I can see that I only have a quadratic. There's only going to be as many as lambda squared right here. So I don't mind going ahead and getting a quadratic equation in those brackets. So I have a lambda squared, and then I have plus lambda and plus 9 lambda, which totals up to 10 lambda. And then I have a -1 times -9, which is 9, plus 20, which would end up being 29. Okay. 29 is not such a nice number to use for factoring anything. So in fact, it does not factor nicely, but I can always get the roots by using the quadratic formula. So that is what I'm going to need to do here. So again, as usual, I set this equal to 0. At this point, we're going to set this equal to 0 and try to solve for lambda. I see that lambda equals 3 is one solution from the factor in front. But then from this quadratic equation, I'm going to get 2 more roots. And what are they going to be? -10 plus or minus the square root of 10 squared, which is 100, minus 4ac is the quadratic formula. 4 times 29 is 116. You guys have to help me out today. I'm suffering a little bit up here. 116, I think that's right. And then all over 2. And if I clean this up, -10 over 2 is -5. And then underneath this radical, I have -16. 100 minus 116. So that's -16. What is the square root of -16? 4. 4i. And then that has to get divided by 2. So by the time I cut that in half, it would actually just be 2i. Okay, so there you go. So you have these lambdas, 3, -5 plus 2i, and -5 minus 2i. A 3 by 3 matrix will always have 3 lambdas. Now, some of them might be repeating, but you have to, when you make your lists, you're going to write down those repeats. So you're always going to get, for a 3 by 3, you're always going to get 3 things here. By the way, do we know yet whether or not A would be diagonalizable? Are we able to answer this question so far, or we have to keep going? Angel?
Yeah. Yes, it is because
That's right. That's right. This is already a yes, guys. This is already a yes. Let me put that over here as well. So A is diagonalizable since no lambda values repeat. There's no repeat. There's no repeats there. What's the point? Why does that mean it's going to be diagonalizable? Well, that just means that all of your m sub lambdas are all 1. The multiplicities, the repeats is only 1. And every eigenvalue will pull a weight of 1, right? So for sure, you're not going to have a problem if there's no repeats. Now, if one of the eigenvalues were to have repeated, then it would be a maybe at this point. Then we would need to go further before we could say yes or no. I would have to figure out, does that repeated eigenvalue really pull its weight or not? But at this point, I just want to take stock. We've already answered the question, and I haven't even found the eigenvectors. I haven't talked about doing the null spaces. None of that so far, right? So very early in the process, because there's no repeats, very early in this process, I have been able to at least figure out that A is diagonalizable. Okay, but the question asks us to do more than that. If so, find S and D. Now, finding S and D is really just a matter of finding the eigenvalues and eigenvectors. We've already got the eigenvalues, guys. In fact, if we want, we could write down D right now. We could write down D right now. We could just go ahead. Here's 3, -5 plus 2i, and -5 minus 2i. By the way, on my sideboard over here, I forgot to mention this. On my sideboard, I'm reminding you about these fun facts about the eigenvalues. If we add up these 3 lambdas, right? if you add them up, the I parts cancel. And you just have 3 minus 5 minus 5, which would be -7. If you add up the trace of A, the diagonal values of A, -1 plus -9 plus 3, that's also -7. That's good. That confirms at least that these are reasonable answers here. I've talked about this a lot. If you get the lambdas wrong, then finding the eigenvectors becomes a real problem. It's not going to work out very well. So it's really important to make sure your lambdas are good. That first fun fact especially is an easy one. It's a really easy one to work with. Okay, so I've got D. Now let's find the eigenvectors. So I'll start with lambda equals 3. And so that means I'm going to calculate this null space. Remember that the eigenvectors come from these null spaces. I have to subtract 3 from the main diagonal. So I'm going to put the matrix A minus 3I right here. And if I subtract 3 from the main diagonal, I have -4, -5, 1. And then on the second row, I have 4, -12, and -1. And then on the bottom row, I have 0, 0, and 0. And just to remind you, this matrix is never going to be invertible. It cannot be invertible when you're doing these eigenspaces. And you can see that there is a row of zeros here. Even if there were not a row of zeros here already, with the use of some EROs, you would be able to get a row of zeros for sure. At least one, maybe more than one. But that's whenever I say, oh, you can always cross off a row, that's what I'm talking about. So in this case, that's the row I'm crossing off. I don't get to cross off anything else, just that one row. And I'm actually going to do an ERO here, guys. I'm going to add row 1 to row 2. So I'm just going to leave. I know it looks a little messy, but if I add row 1 to row 2, the -4 and the 4 will add up to 0. So I'll have 0, -17, and 0 there. And then we still have this row of zeros on the bottom. And I can kind of circle some pivots now. At least some pivot positions here in my matrix. My unknowns would be thought of as X, Y, and Z. And you can see that Z is free because there's no pivot in the third column. So I'm going to call that T. But if I look at Y, take a look at that middle row, -17 times Y equals 0. So actually Y has to be 0. So Y is already 0. And then if I want to figure out what X is, I come back to the first row now, and I say, well, -4 times X minus 5 times Y, 0, plus Z should add up to 0. Let's just write it down. This is the first equation in our system here. But I already know that Y is 0. And so if I solve for X, it's just going to be 1/4 of Z. So in other words, 1/4 of T. Okay, and so busting out the T, I'll get my eigenvector. So the eigenvector is 1/4, 0, and 1. Did I do that okay? So the X is 1/4 of T. And then the Z is equal to T. And there is no Y there because of the second row, right? The equation on the second row is just -17Y equals 0. Is everybody seeing how I'm getting this? Edgar?
We're not writing them as basic, right?
I'm not really thinking of it as a basis. This is a basis for the eigenspace, but we don't need to list it as a basis here. I guess that's true. Earlier in this chapter, I was doing that. For the purposes of what I'm trying to do right now, which is to write down what S is, I just need to get these vectors written down. Yeah. Any other questions so far? You guys okay over there? You sure? Okay, just making sure. Okay, so that's my first eigenspace. Now let's go to the second one. We have lambda equals -5 plus 2i. So this is going to get a little messier because of the imaginary numbers, but we're going to take another null space here. And what I have to do is subtract, let's do this very carefully. Watch the signs. I have to subtract -5 plus 2i from the diagonal values of a. So on that upper left corner, I have a -1. And from that, I'm going to now subtract -5 plus 2i, which actually gives me +4 minus 2i. Okay? And then the rest of the first row just gets recopied as it was given. On the second row, we start with a 4. The second entry over there, it's -9. And from -9, I have to subtract -5, which brings it up to -4. And I also have to subtract 2i. So we would get -4 minus 2i and then -1. And then the bottom row, we have a 0 and then a 0. And then we have 3. And from 3, we have to subtract -5 plus 2i. So that becomes 8 minus 2i. Okay. I wanted to do this warm-up problem because I don't think I had maybe shown quite enough practice on how to deal with these kind of null spaces for 3x3 matrix when it's got imaginary numbers in it. But you know what? This is super easy. It looks not so good. Let's first of all remember that we have to be able to cross off a row. And you can actually cross off any of the 3 rows that you would like here. I would recommend crossing off a row that looks bad to deal with. I actually kind of like the bottom row. The bottom row has a lot of zeros in it, so as usual, we have X, Y, and Z here. I'm going to cross off the middle row. I know that when I cross it off, what I mean is I'm going to imagine that I did EROs and got it to 0, 0, 0. So it would become 0, 0, 0. I have to trust that. I'm trusting that that will happen because this is not an invertible matrix. So I trust that that will happen. So far, so good? The reason I like row 3 is that row 3 is super easy to work with. 0 times x plus 0 times y plus 8 minus 2i times z is equal to 0. And so this is gone, and what you have is some number times z equals 0. So that actually tells you right away, guys, that z is equal to 0. The third row tells you that z is 0. Yeah.
Richards, and you also cross it, or do you have to perform EROs?
You don't need to do any EROs here. You mean crossing the middle row? No, you just cross it. Just cross it off. Yeah, just cross it off. Now, I already have figured out that z is equal to 0, correct? So if I now go back to the first row, I know that equation doesn't look so nice. I'm going to write it down. 4 minus 2i times x minus 5 times y plus z adds up to 0. But remember, guys, z is already gone. The z is already equal to 0. So all that you actually have here, guys, is this little equation. And somebody was asking me in office hours, I think, can I do that A-B trick thing? Remember that little trick I showed you with A and B, where you can just write down the vector immediately? Somebody asked me, well, can I do that for a 3x3 matrix? And the answer is, if you have already solved for one of your unknowns, and it's already kind of out of the picture, then the remaining equation here, you can think of that as the A and this is the B, and you can play that game with those 2 unknowns. So in this case, the 2 unknowns are x and y, and you can do that. So what I could do here is I could say, oh, well, for x and y, I'm going to remember how the A-B trick works. You swap the 2 entries, and you change the sign of one of them. So I'm going to take this, I'm really just looking at these 2 numbers. This is A, this is B. And I'm going to put B first, but I'm going to do a sign change on it, write it as 5, and then I put A second. So remember how that trick works. The vector is, negative B and A, for example. That's that A-B trick. And when I explained it to you originally, we were only looking at a 2x2 matrix. This one is a 3x3, and I'm still able to use that trick. So I've got x, I've got y, I've got z. I'm going to write down my vector now. So my vector, I'll call it v. My vector is 5, 4 minus 2i and 0. That's the eigenvector for that eigenvalue. Okay. All right, so it's kind of clever how to do that little trick with the 3 by 3. Finally, we have one more eigenvalue. I'm going to do this kind of quickly. The final eigenvalue is lambda equals -5 minus 2i. And I talked about this, that when you have a pair of complex conjugate roots, once you have found the eigenvector for the first eigenvalue, then you can just write this one down by conjugating. I didn't prove it, but I basically said that you can immediately write down what v is by just taking this vector and conjugating each of its slots. Conjugate just means change the sign on the I parts. So the 5 is going to stay as a 5. But the 4 minus 2i will become 4 plus 2i, and 0 will just stay as 0. So this is what you would end up with right here. And guys, that's the third eigenvector that you need to finish filling out your matrix S. So S would be, so now I'm going to write down what S is. Now guys, remember, the S has to go in the correct alignment. If you put the eigenvalues in this order, then you have to put the eigenvectors in the compatible order. So for the first eigenvalue was 3, so I'm going to put 1/4, 0, and 1. And then the second eigenvector is 5, 4 minus 2i, and 0. And the third eigenvector is 5 and 4 plus 2i, and 0. And this is your matrix S. And so we found S, we found D. It's a diagonalizable situation. And so we're good to go. Any questions on that? Yeah, Vinny?
Yeah, the AB trick on the 3 by 3 matrix
Yeah.
only works because one of the variables was 0. Or would it work if it still would have been like a?
It needs to be 0. It does need to be 0 here, yeah, because in order for you to be able to just swap the A and the B and do a sign change on one, you need this to still cancel out to 0. So that is a good point. That is a good point. Guys, to some degree, you have to trust whoever's writing the question. Don't know who that would be. To make sure the matrix is reasonable, right? There has to be some zeros in this matrix in order for it to work out nicely. So, okay. Good deal. Any other questions about this? I'm glad we did one more semi, complicated example of it, just to make sure you can kind of see what to expect. Okay. One other thing I wanted to go over that I think kind of slipped through the cracks last week while I was gone is, what if I ask you to, so if I just hand you a matrix, you usually cannot just look at it and tell me what the eigenvalues are immediately. I don't think anybody looked at this matrix and knew that the eigenvalues would be -5 plus 2i, -5 minus 2i, or 3. So the question I was wanting to talk about for just a minute with you is, are there certain matrices where you can just immediately see what the eigenvalues are straight off of glancing at those matrices? Does anybody think they might have any ideas about that? Oh, the triangular ones. Yeah, that's awesome thought. Yeah, let me make a remark here about that. So this is a different topic. I don't think we wrote this down before. If A, which is n by n, is upper or lower triangular, then what's so nice about that is that means that when you're doing the characteristic equation, right, when you're doing the determinant of A minus lambda I, you're talking about the determinant of a triangular matrix. And the determinant of a triangular matrix is just the diagonal entries. right? So in this case, then the eigenvalues lie along the main diagonal of A. So you'd be able to just read them off. So as a example, I could ask you to write down a 4x4 diagonalizable matrix with, let's just say, 10 non-zero entries. I'll make something up here. So I just want to make an example. And there will be many right answers to something like this, but you're going to write down a 4x4. And if we make our matrix, so a 4x4 matrix, by the way, has 16 entries in it. 16 entries here, but I'm going to be forced to make, if I want to make this a triangular example, which is kind of in the spirit of my remark, if I want to make this into a triangular matrix, I'm going to have to use up 6 of the 16 entries of this matrix as zeros. So the way I'm starting this off here, I'm hoping to come up with an upper triangular matrix. So I said there needs to be 10 non-zero entries. I've already got 6 zeros on the board, and I've got only 16 total numbers to play with. So I've got to make sure that all of the rest of those entries are not zero. And I'm wondering if anybody has any suggestions for how to finish filling out the matrix. Would this work? Would that matrix be a good example to use? What's the remark say? Remark says, if the matrix is triangular, such as this one, then the eigenvalues are on the main diagonal. So what are the eigenvalues of this matrix?
4, 7.
7, 7, 7, and 7, right? Is that going to be diagonalizable? That would actually be a maybe. Remember that if the eigenvalues repeat themselves, then we have to check whether they pull their weight or not. So I don't know whether this one works unless I actually now go to the hassle of looking at the null spaces. Well, it would be one null space here, right? So this one, this is not the best example, right? It's not the best example. In fact, it does turn out it's not going to work. This matrix will not. This eigenvalue has a lot of weight to pull, and it's not going to do it. Okay. So can somebody think of a way that I could just get the answer and just go home and say, yeah, it's obviously going to work? Huh?
Probably just put 1 between 4 and main diagonal.
Yeah, why don't we just make sure that there's no repeats on the main diagonal, right? So we're still going to put all these zeros here. And then I actually don't care what numbers you use over here. This actually doesn't even matter. If I write down this matrix like this, then your lambdas are 1, 2, 3, and 4, and there's no repeats. No repeats. And in that case, if there's no repeats, then everybody pulls their weight, guaranteed. No repeats, and so this one does work. Okay? So the moral of what I'm saying here, guys, is if I ask you to give me an example of a matrix that's diagonalizable, I would suggest that you use a triangular matrix and you make the diagonal entries of that triangle all distinct values, no repeats. Okay? Now, here is a question, and we're going to do this in the group work that I just handed out to you guys, but I'm going to put it here as a natural question. If A and B are diagonalizable. So I'm gonna call this a true false question. If A and B are diagonalizable, then A plus B is diagonalizable. This would be kind of a natural question. And I put this on my exams many times. It's a little one of those theoretical problems. Okay, if I add two diagonalizable matrices, will I get something diagonalizable? Except I think I told you that I stopped doing true false on my exams. I don't like those anymore. I will tell you that it's false. And then just ask you to give me an example. Okay, well, if I'm asking for an example, then I have to come up with like, what would A be? What would B be? And kind of go from there. What size matrices do you think would be good for an example? One more time. 2 by 2? Yeah, 2 by 2 is exactly what I would suggest. So I would suggest a 2 by 2 and a 2 by 2. And I want to make this easy on myself. I don't want to just pick 4 random numbers right now. I want to make sure that A is diagonalizable. So does anybody want to suggest? Let's just do this together as a group. I was going to do it in the group work, but I'm having too much fun. Can somebody suggest a matrix here for me?
0, 0, 1.
1, 0, 0, 1, 2. Ah, okay. This is triangular, isn't it? I mean, it's both upper and lower triangular, actually. So the lambdas here are just the diagonal values. The eigenvalues lie on the main diagonal. And if the lambdas are not repeating, that's good, right? So this is diagonalizable. Okay, and then I have to do another matrix kind of the same way. So maybe I'll make this one also triangular. And I need to put some numbers here. 3, 0, 0, 5. Okay, so we could try that. So if I do this, then I'm going to get my eigenvalues of 3 and 5, and that's going to be diagonalizable. Okay, but now what about A plus B? So the trick is we would like to look at A plus B and see whether that's still diagonalizable. Well, if I do my slot by slot addition, if I add these matrices together, I get 4, 0, 0, 7. And what are the eigenvalues here? 4 and 7. Is this diagonalizable? It still is, right? Now, wait a minute. I wanted to give an example. I need to tweak this because this is not going to work. I need an example where the A plus B is no longer going to work. In other words, where the A plus B is not diagonalizable. Would anybody like to suggest a modification for the matrix B that could help us out here? Yeah,
Make the 3 a 2 and make the 5 a 1.
So turn this into a, maybe instead of a 3 and a 5, how about a 2 and a 1? Okay, so this is still good. Now my lambdas here are 2 and 1. And now when I add these together, these numbers are going to change. We're going to get 3 and 3, right? So now what are the eigenvalues of this matrix?
3, 3.
3 and 3. Ah, we have a repeated eigenvalue. So does that mean we're good to go? Remember that if the eigenvalue repeats, then it might pull its weight. It might pull its weight. I want to check this. I want to check this matrix here. 3, 0, 0, 3. Does that matrix, does the eigenvalue lambda equals 3 actually pull its weight? Let's just try this one. Lambda equals 3. I'm going to do the null space. Null space of what? Of the matrix I get when I subtract 3 from the main diagonal of the matrix. Well, when I do that, I'm talking about this null space now. The null space of all 0. Oh boy. How many free variables do you see there? There's no pivots, which means there's two free variables. Y is equal to T, X is equal to R, and when you bust that out, you'll get a 1, 0 out of the R, and you'll get a 0, 1 out of the T, and that does pull its weight.
Oh.
Which means that even though this eigenvalue did repeat itself, it did pull its weight, which means that the matrix is still diagonalizable. I still don't have a good example yet. We're getting closer. Can I get a suggestion how I could edit or modify either of the two original matrices just a little bit more so that I won't get this eigenvalue to pull its weight?
Give upward triangle.
Well, these are both technically upper triangular, but I think I know what you mean. You want to put,
Instead of the 0 in the corner, have an actual number.
I would put a different number up here. Yeah, how about a 1? Let's make a quick, or you could do it with the matrix B, it doesn't matter. Putting that 1 right there does not change the eigenvalues of A, because it's still triangular. And so it's still a diagonalizable matrix. B is still the same, but now when I add these together, see, this is what Vinny was noticing. We put a 1 there. And now when I subtract the 3 from the main diagonal, we put a 1 there. Now that's a pivot. Now we don't have a free variable anymore on the Y, I'm sorry, yeah, the Y is 0, only the X is free, and this is all we get. And so now this one is not diagonalizable. That makes some sense? It took us a couple tries, but for examples, guys, 2x2 matrices are awesome. Triangular matrices are great because you can control the eigenvalues. They are just along the main diagonal. And you just had to tweak it a little bit to kind of get the features of the example that you wanted. Edgar?
If you make the first two negative, like -1, 0, 0, -2.
-1, 0, 0, and what was this? -2?
I meant keeping that one and then making B that matrix.
So this here, oh, was that a 1?
That was a 0.
Oh, okay. I'm sorry. Can you just tell me what you want?
Yeah, it's 1, 0.
Don't take notes on this, guys. 1, 0,
0,
0, 2. All right.
and then the other one is -1, 0, 0, -2.
Great. Those are both diagonalizable because there's distinct lambdas. When I add them together, the result is all zeros. But we've already seen what happens when we use all zeros in the null space. We get two free variables and the matrix does pull its weight. So that would actually not have worked as a counterexample. Yeah. By the way, what does this prove about diagonalizable matrices? The fact that we have an example where A and B are both diagonalizable, but their sum is no longer diagonalizable. Is that a concept we've heard elsewhere in this semester? That we could frame that? So I've got one vector that's good to go. I've got another vector that's good to go. I add them together and it's no longer good to go. Was that some concept from, say, I don't know, maybe a month ago?
Determinant.
Not determinants, a little bit after determinants. The set of diagonalizable matrices does not form a.
No Spain.
What was the word?
Spain.
I heard somebody say it. Subspace. Subspace. Remember the closure under addition?
Oh.
One of the first things if you want to know is if a set of vectors forms a subspace, it's got to be closed under addition and closed under scalar multiplication. Well, diagonalizable matrices do not do that. They are not closed under addition at all. So the answer is, so maybe I should add that here. So the set of diagonalizable matrices, I know this is combining it with a different concept. The set of diagonalizable matrices, a little bit more room here. does not form a subspace. In this case, it would be a subspace of M n of R, whatever the size of the matrices is. It does not form a subspace. Closure under addition fails. Yeah, kind of a nice example. Okay. Before we go to the group work, I'm just having too much fun with this. Can I do one of your homework problems for you?
Yes, please.
Nobody put anything on the board yet, but I'm gonna do one of them for you right now because it's actually very instructive. So, unless there's any follow-up with this. Everybody good? Ooh, I love writing questions that are like this. This is a good thing to be sure you're comfortable with. And practice a little bit more. Let's go to one of the homework problems. I'm gonna do number 9 from section 7.3. This is the homework that's due tonight, okay? And so they give you this matrix A, which is -2, 1, 4, -2, 1, 4, and -2, 1, 4. That's the matrix. Okay. And they are gonna ask you basically the same question as the warm-up. Is it diagonalizable? And if so, I think it asks you to find S and D, all that good stuff. Okay, so is A diagonalizable? Now, here's the thing. Here's the thing about this example, guys. Unlike the warm-up, where there was a nice row where we had some zeros we could take advantage of, you notice that I've been a little bold here and I've given you a problem that has no zeros in it. The matrix has no zeros in it. It turns out that you can still do a cofactor expansion. I even had somebody, I think, came into my office the last couple days and had gotten the correct values for the lambdas. But you would have to be very careful. You'll get a cubic equation that you would then have to factor very carefully to get the lambda values. What I wanted to do in my solution for you today here, though, is show you a clever way to get the eigenvalues without even doing the characteristic equation. I'm going to do a workaround to come up with the lambdas. I'm going to do a workaround for you. Okay. Is there anything that you notice about this matrix? One more time. The rows are all the same. Okay, so what does that mean? If we did EROs, what would happen? We get a row of zeros. If we just take this matrix and do EROs, we will get a row of zeros. What does that tell you about that matrix? It's not invertible. It's not invertible. That's exactly what I was looking for. So note, A is not invertible. Right? Since all 3 rows are multiples of each other, right? I'll just mention that. All 3 rows are scalar multiples. Well, actually, let's just say all 3 rows are the same. When you've got 3 rows that are all the same, then I'm pretty sure it's not going to be invertible. If it's not invertible, then what is its determinant? The determinant of a matrix that's not invertible is 0, right? Based on that, does anybody know what one of my lambda values is?
0.
0. Why is that? If the determinant of A is 0, why does that mean that one of my lambdas has to be 0? The answer is somewhere in this room. If the determinant of A is equal to 0, then why does that mean that one of my lambdas has to be 0? Can I back up any further? Yeah, right here. The fun facts, right? the fun facts, if the determinant of A is 0, then when I multiply all of the lambdas, I have to get 0. Well, that means one of them has to be 0. Okay, now, I would ultimately need to come up with 3 lambdas. But you know what? I'm just gonna start with what I have so far and work on it. So this is my lambda. I'm gonna do the null space for this lambda right now. Okay, so I subtract 0 from the main diagonal, which means I don't do anything to the matrix. So you're literally just doing that, subtract 0. And I know that I have to be able to cross off a row. I would like to point out here though, however, you can actually cross off 2 rows because all 3 rows are the same. So you can get rid of 2 of them. I've got my pivot right here. And so I've got X, Y, Z, and I'm gonna have a free variable for both Y and Z. So let's write that down. Y equals T, Z equals, sorry, let's start with Z. Z equals T, Y equals R. And now I have to solve for X from the first equation. So negative 2X plus Y plus 4Z, that has to equal 0. So if I solve this for X, I'm gonna get X equals 1/2 of Y plus 2 times Z. So that would be 1/2 of R plus 2 times T. And I'm gonna bust out my variables on this. And I'm gonna get 2 vectors here. When I bust out the R, I get 1/2, 1, and 0. And when I bust out the T, I get 2 and 0 and 1. Okay. So that's great. I've come up with the first eigenspace. With this eigenvalue of 0, I came up with these 2 eigenvectors. Does that actually shed any more light on the remaining lambdas that we have to still figure out?
They'll be repeating.
Pardon me?
They'll be repeating.
Okay, guys, this eigenvalue produced 2 eigenvectors. Would that have been possible if 0 is only an eigenvalue one time?
No.
I mentioned this, and I know I did it kind of quickly in passing, but one thing I told you guys when we were going over this theory is that no eigenvalue can ever overpull its weight. Right? We talked about for a defective matrix, there'll be an eigenvalue that doesn't pull its weight, and I proposed, well, would it be possible for some other eigenvalue to make up for that by overpulling its weight? Turns out the answer was no. I said it was no. And so if this eigenvalue only shows up once and produces 2 eigenvectors, that would be overpulling its weight. That can't happen. So you know what? Not only is 0 an eigenvalue, it's got to be an eigenvalue at least twice. At least twice because it produced 2 eigenvectors, you see? Now, if this was actually an eigenvalue 3 times, then the matrix would be defective. Because we've only got 2 eigenvectors there, but once we have 2 of the lambdas, can we figure out what the third one is?
Yeah. You can use the.
I've got the other fun fact. When I add up all 3 lambdas, it has to match up to the trace of the matrix. If we do the trace here, the trace is the sum of the diagonal values. If we add those up, -2 plus 1 plus 4, that adds up to 3. So my 3 lambdas have to add up to 3. 2 of them are 0, so the third one has to be 3. The third one has to be 3, exactly. And so now we have a null space here. And this will finish it off. I subtract 3 from the main diagonal of A, I get -5, 1, and 4. -2, -2, and 4. And -2, 1, and 1. I think I did that right. And remember, we have to be able to cross off a row. This matrix cannot be invertible. We have to be able to cross off a row. I don't really have a strong opinion. I might get rid of the first row just so I can work on the -2s a year a little bit. But it doesn't really matter. So with this one, I might just suggest that we take the middle row and put it on top, but cut it into, basically divide it by -2. So I'll do that, and then I've got a row of zeros that'll end up showing up on the bottom here. So go ahead and leave the bottom row the same, but put it in the middle like that. And I gotta do one more ERO. I'm gonna take the first row and leave it the same. And then I'm gonna take 2 times the first row and add it to the second row. I'll get 0, 3, and -3. And then 0, 0, 0, right? There's a pivot, there's a pivot. Man, we've done a million null spaces in this chapter. So there's a lot of them to do. So Z is gonna be a free variable, right? Z is free, and so then we find out what Y is. Y has to be equal to Z if you look at the middle equation there, so that would be equal to T as well. And then the first equation, actually, I'll let you guys work it out, it also has to be equal to T. All 3 of them are equal to T. When you bust out the T there, you're gonna get your eigenvector 1, 1, 1. That turns out to be correct. 1, 1, 1 is a good eigenvector. And so, yeah, so we're in good shape now. We can write down what S and D are. Any questions so far? There's a lot of content in this example. Like that's why I wanted to do it. There's a lot of good stuff to review. So let's write down what S and D are. The S is just that we take all of the eigenvectors. So we have 1/2, 1, and 0 for the first column, and then 2 and 0 and 1 for the second column, and then for the third column, 1 and 1 and 1. And then for D, we have a diagonal matrix and the lambdas are going down the diagonal. So we can just put 0, 0, and 3 as our lambdas, and that's our D. So we get S, we get D, and that's all we have to do on this problem. We don't have to multiply anything out. We don't have to find S inverse. Just says find S and find D. Yeah. Questions? Okay, like I said, if you wanted to, you could have figured out these eigenvalues by just brute forcing it with the characteristic equation. But I thought this was kind of a nice example to review how the fun facts could be useful and also how invertible. Oh, by the way, guys, problem 1B on the group work that we're going to do after we take a 10-minute break says, give an example of a matrix that's diagonalizable but not invertible. I think we just did one. Right? It's diagonalizable because we found S and D, but it was not invertible, as we pointed out earlier. It's turning into 0. So anyway, easy to give examples like that. How's everybody doing with this? How am I doing? Do I seem different than normal today or like my usual self?
Yeah.
Even more excited? Maybe I should get sick more often. Anyway, I think this is a good time to take a 10-minute break. Let's stretch our legs, get some fresh air if you'd like. And then if there's any other homework problems that you want to throw on that board over there during this 10 minutes, would be a good time to do that. And then we'll be back up at about 10 after. Anthony, could you do me a favor?
Yeah.
Would you mind just erasing the boards for me?
Yeah.
Now that'd be great, because I need to go take a break. Oh. Yeah, if you only had one free variable, but you would only get one vector here, and it would be defective. You would stop at that point.
Since you got 2, because I kept 2 feet variables.
Yeah, it's really because you have 2 free variables here. What's going on up here doesn't matter. just this part here.
But this defines like if there's two, then we have two.
Well, it just means that both of these vectors have a non-zero entry in the first slot. That's not really the main issue. The main issue is you have two variables here. The eraser may work better for you. I don't know. It's up to you. I really appreciate it.
Yeah.
Why you? Washington. Except my friend, he's like, take another year, I'm like, nah.
Oh, I thought it was.
That's the only one I need to know. But join McNair's program, bro, I'm like, I'm good.
You got to research too.
Exactly, I'm like.
What about you?
Research I'll be doing, it isn't gonna be like led by me, it's gonna be led by the professor.
Yeah, exactly.
Oh, we get
Is there, you know, is there that one? Yeah, did they do that? Oh, no.
Sorry. Someone.
You're not gonna like it.
Yeah, everything.
Submitted it before the like the deadline.
Yeah.
Like, so hard work and over like stuff like
Yeah,
that.
yeah.
I was sick. There was more experience, so
Yeah. Ours is like Korean.
Right now, I'm with you. I like, I wish you check sooner, you know, because it both. Yeah. Like if you do that sooner, then I'll figure that out. Yeah. Yeah, like that.
Yeah. You got brittle.
Anyways, what were you saying?
You guys put that on my.
Oh, no, it's just.
How scary.
When they're new grad.
Yes. That's part of it.
Yeah.
Oh, there you go. There you go. Finally, no one did that. Yeah, bro, he's rotating.
Yeah, we're getting the joints.
You're short, I'm shorter.
Yeah, you put
I should say, I'll say, beat the house and like. Oh, that shit was long time ago, like.
I was only
This anymore.
No.
It's even not how long.
Oh.
Like, everyone has to leave. It's just always funny. Yes.
Yeah.
I think she was more treated than.
Get it.
It's huge. That's what when that happens.
He's good.
I think like all those like the pussy device from the.
How many floors?
You have to have the release.
Yes.
Like they have a bunch of like they also have to pick. 4 foot 1.
I don't think it's
Taking that next one.
I didn't even know.
Taking 170. I saw there a real free like this. Guys, I'll just do it for fun. No, I don't know what's happening.
Yeah. You're nice and. Like, is this what I signed up for? It's
So what did she give? How did you like
Is it really?
So it's actually 320.
Wait, are you sure? I'm just
Yeah.
Well, they're still going to.
Construction site on it. They're like, hey, what do you?
You know, the reason. And so because you're at.
Yeah. So. Keeps you up at night. It's one of those things, you know.
Yeah.
Oh, shit.
Well, I can talk.
You only got a good picture.
And then my, yeah, I took it like last week. I got like, my pointless, and my breath. There's.
No.
But
No, not anymore. But I work at the parks. Oh, yes.
It's the, yeah, stuff like some of that flavor actually. It's just getting into like this.
Yeah. Later, more time.
Wait, so where did you work all this?
I took one first and then the pandemic. That was the last time.
all of these, like,
Like, I was like, I was just sick. I was almost sick. Yeah. I had to like spin it, so I was like. And I couldn't do it. And I'm just like. Top of it.
I'm just gonna let all the
All right, guys, I think I have given myself enough of a break. The rest of my voice here to maybe be able to start again. Hopefully, everything makes sense. I don't see any problems from 7.3 up there on the board, so I'll take that as maybe a good sign, but I do have office hours later today. I don't promise to be more than half awake by this evening, but I'll try my best to help you if you do think of any questions before you turn in the homework. Before I go to the chapter 8 stuff, just really quickly, this group work that I passed out, does everybody have a copy of that? Kind of in front of them somewhere? I think I had a chance to get it out to everybody before class. I think since we already did half of it, I'm just gonna quickly finish it up with you guys really quickly. So this is just the group work, and we've done examples already for 2 of the 4 parts in the group work, and I just want to talk about the other 2 parts really quickly. So let's do the easy one first. Let's do problem 2A from this group work number 11. I'll read it out loud and then it's a true false, so we'll take a vote in a second. I'll literally have you raise your hands. So it just says, if the eigenvalues of a 3x3 matrix are -1, 3, and 6, then A is non-defective. Okay, so let's just read it one more time. 2A, if the eigenvalues are -1, 3, and 6, then A is non-defective. Okay, that's true or false is the question. So let's do a quick straw poll vote on this. Why don't you raise your hand boldly if you think it's true? Guessing? Okay, great. Does anybody think it's false? Not so much. There's a lot more people thinking it's true. Why is it true? Those of you who think it's true. It's diagonalizable, it's non-defective, but why? There's no repeat eigenvalues. That's it. Yeah, so this is definitely true. True, there are no repeat lambdas. Remember, the only way that a matrix could be defective is if there was a repeat eigenvalue that did not pull its weight. So that one's definitely true. It would be non-defective in that case. All right. The other one that we didn't talk about yet, but which I would like to here, is to give an example of a matrix that is invertible but not diagonalizable. So we already gave an example that was diagonalizable but not invertible with one of the homework examples, but this is the other way around. Can we write down a matrix that is invertible but not diagonalizable? So there will be a million answers here that would work. What size matrix for our example do you think might be good? 2 by 2. And are there any particular thoughts you have about constructing an example for this matrix? When we did the example earlier, what was our main objective, or how did we try to approach that? Angel?
So being vertical, we don't want the determinants to be like.
True.
Then not diagonal.
Not diagonalizable.
So we do need.
We need to have a repeat lambda, right? So what kind of matrix could I use so that I could get my lambdas easily? That's a very specific example. I want to build up to it slowly. What was the observation we were using earlier in terms of making an example of matrix where you can just read off the eigenvalues? Make it triangular. Exactly. So let's just go with upper triangular again. So I'll put a 0 in the lower left corner. Now, Angel's comment was that if this is going to be not diagonalizable, then we have to have the same eigenvalue twice. So, Tiffany, what's your favorite number? 8? All right, good. So let's use 8. I gotta use it twice because I want the lambda to be 8 and 8. And by the way, guys, you might notice that this matrix is already going to be invertible. The determinant of this matrix is going to be 64, which is not 0. So it's invertible. I just have to make sure that this is not diagonalizable. And what might I want to put in that upper right corner to make sure that it's not going to be diagonalizable? How about a 1? Any number other than a 0. Anything other than a 0 would work. Yeah, that would be a great example. This matrix is invertible, but it's not diagonalizable because the eigenvalue is not going to pull its weight. If you subtract 8 from the main diagonal, you will only get one free variable in the null space that comes from that, and that won't be enough to pull the weight of an eigenvalue of multiplicity 2. Great. So you can make these examples using 2x2s really easily. I think it's a good way to do it. And so there you have it. That's a wrap on group work 11. Okay. Questions on any of that? Okay. Well, let's take a breath and switch gears here then. I see those homework problems there, and it'll be perfect. We can talk about them in the context of chapter 8 here. The first section of chapter 8, we talked about it mostly on Thursday last week. We have our nth order linear differential equation, right, which we wrote down literally the first week of the semester. And last week I introduced this D notation. The D is just the capital D just stands for the derivative operator. Okay. So anytime I see a D or a power of D, I'm talking about taking derivatives of the unknown function y. And so we can rewrite our differential equation in the D notation. And I compressed it even more last Thursday by calling that entire operator L. So my differential equation, the thing in the box here, which is really ultimately what we're going to be focusing on, is very compressed. L of y equals F. And the goal for this is just going to be to solve for y, which is the unknown function in our differential equation. That's always the objective, is to solve. When we're solving differential equations, we're trying to find the unknown function. Okay, so just to remind you, it turns out that in order to solve this, the first step in solving one of these nth order linear differential equations is going to be to solve the associated homogeneous nth order linear differential equation first. So we're going to get more into that on Thursday, but for today, the point is just that you're going to forget about the capital F and replace it with just 0. Yeah. So you're just going to talk about this equation here, L of y equals 0. And we're going to learn how to solve these kinds of equations first. And then we'll use that to bolster ourselves back up to solving the non-homogeneous differential equation that we first derived in this first box. Okay, so we're going to start here. We're going to start here with 0 on the right-hand side. And we made the remarkable observation last time that if we focus on the homogeneous differential equation here, and we're trying to solve for y, that actually what we're looking at is the kernel of L. Going back to the linear transformation chapter, right? The kernel is consisting of those vectors that get transformed to 0 under the transformation. L is my transformation now, or my operator, as it's often called in this particular subject. And so L of y equals 0, if we're trying to solve that, then we're actually just trying to find the kernel of L, which we already know forms a vector space. From chapter 6, we learned that. The kernel of any linear transformation is always going to form a vector space, and there's a theorem that actually tells us what its dimension is, which is n. So this second differential equation here, the one in the second box, turns out to not be quite so challenging for us. We actually know that the solutions to this this guy right here, the solutions to this guy right here, they form a vector space of dimension n. And so if we can just come up with a basis, we'll be able to span all of the solutions to our differential equation as linear combinations of that basis. It's really the linear algebra, guys. I'm super stoked about this, that we are now seeing the linear algebra playing a major role in trying to come up with solutions to differential equations. So that was just the background of what we kind of started last time. I think I'd like to do an example of one of these because we haven't really done an example yet. Let's try to solve our first, are you ready for this? We're going to solve our first higher order differential equation of the entire semester. I'll do it right now. Let's solve d squared plus 1 of y equals 0. When I say solve, that's just my shorthand way of saying that I would like to find the general solution to that differential equation. So when I say solve it, I mean find the general solution. Okay. Can somebody tell me what is the order of this differential equation? What is the n here? 2, right? The highest power of d that you see is 2. So this is actually a second order differential equation. If we wanted, we could go back and rewrite this equation without the d notation. 2 derivatives of y would be y double prime, and then plus 1 times y would just be y equals 0. So we could certainly write it either way. They're totally equivalent. One of them is in the d notation. That was how it was given to us. This is more the traditional notation that you would have seen it in calculus. And I am wondering whether anybody just sort of willy-nilly off the top of their head can think of a solution to this. Do you remember in calculus, can you think of any functions that you ever would have seen in calculus where after you take 2 derivatives of that function, it cancels out with the original function again? One more time. E to the x, when you take derivatives of e to the x, you just keep getting e to the x, and then e to the x, and then e to the x. They don't actually cancel out, they kind of combine together. But yeah, I'm thinking of something like that. Marco? Or Omar, I mean?
Okay, the sine and cosine.
How about the sine of x? What happens when you take the derivative of the sine of x? Well, you get cosine, and you take the second derivative, you get negative sine. Exactly. So solutions include y1 of x equals, if you don't mind, I'm going to put cosine of x first. So if you take 2 derivatives of cosine, you'll get negative cosine of x. And so when you add that back to cosine of x, it does give you 0, right? And the second one that was also pointed out is sine of x. That would be the sine of x. Now, guys, we are finding, we are working with a homogeneous differential equation. So we are solving right now for the kernel of L, which is supposed to be a 2-dimensional vector space. And look what I've come up with. 2 solutions. Are they linearly independent? Because for a basis, they would need to be Li. Let me just, before I go any further, we found 2 solutions. We're doing pretty good here. Why am I not just already throwing a party about this? Well, the problem is that there might be more solutions. And in fact, there will be more solutions. And the question is, when are you going to say enough is enough? I found enough solutions, right? We have to know that we have all of the solutions to our problem. And if we could just figure out that this was a basis for all of the solutions, then we would know that every solution is expressible or buildable as a linear combination of these 2. Because that's what a basis is. It's a spanning set that's Li. So that's why I care about this, right? The remarkable thing here, guys, is not that we found these solutions, although I don't mean to, this is awesome to come up with the solutions, Omar, right? But that's something we could have done 3 classes ago. I mean, 3 courses ago. Back in Math 150A, if somebody gave you this, you could have probably figured it out. What's cool though, is not so much that we came up with these 2 solutions, but actually that those 2 solutions will build all of the rest of the solutions. You don't have to go home tonight and wonder, I wonder if I could make a solution using the E function or using an arctangent, or maybe somehow there's a way to do it using a square root, or maybe a combination of all of that stuff, right? How do I know there's not some weird, crazy function out there that we just don't think of yet, where 2 derivatives of it cancels it out to 0, right? I don't want to be up at night worrying about that. I don't want to wonder, have I missed some solution that hasn't just come to me, right? The good news here is that these are Li, and so they are a basis, because remember, it's 2-dimensional, and I've got 2 linearly independent solutions here, so they span the space, right? Remember that whole thing? K versus dimension. So here K equals 2, the dimension is 2, all right, they match up. So it's both or neither, right? Going back to that chapter 4 material, it's both or neither, and it's gonna be both as long as they're Li. And I claim that they are, so cosine of X, sine of X is Li since, does anybody have a reason? Usually what we do for this is we take our vectors and we lay them into the columns of a matrix and take some kind of a ERO process. I don't really know how to put these into the columns of a matrix. But since it's only 2 vectors, was there a shortcut for Li? 2 vectors would be Li if and only if they are what? They're not multiples of each other. Exactly. I think all of us would agree that these are not multiples of each other. So they are, in fact, they're shifted versions of each other. They don't look like multiples at all. But since they are not multiples of each other, that's right. They are not multiples of each other. So that's awesome. And so that means that we have a basis. So thus, this set forms a basis of solutions to the differential equation. Yeah, they form a basis then. It makes a basis. Well, if it's a basis, then it's a spanning set, meaning that all of the elements in the kernel, all solutions to our differential equation are just linear combinations of those 2. And so thus, the general solution is y of x equals, a linear combination would look like C1 times the first vector, which is cosine of x, plus C2 times the second vector, which is the sine of x. And that would be the final answer, actually. That would do it. That would do it. Make a little bit of sense? So these are 2 solutions to the differential equation. Let me give you another one. Another solution would be 5 times cosine of x plus 11 times sine of x. Another one would be 17 times cosine of x minus 3 times sine of x. any constant times cosine of x plus constant times sine of x will form a solution. There are infinitely many solutions here, but they are all spanned by just these two. Yeah, that's the point. That's the point. We don't have to go home and lose sleep at night thinking, I wonder if there's some other solution that's not like that one, like these. Could there be some other function we didn't think of yet that is important for our real world problem? The answer is no. This captures all of them. These two solutions form a basis for all of the solutions. We don't have to look any farther. Yeah, so that's really the beautiful thing about it. I love it. Without the linear algebra, if I tried to teach this in January, I mean, I probably could have thrown this equation on the board in January. I probably could have had everybody come up with these two solutions, right? But I wouldn't have been able to do anything else with that. I would say, okay, you guys found two solutions. Great, so what? There could be 5 billion others that we just don't know how to find. Now we actually know that no, all of our solutions are actually combinations of those two. I think it's pretty neat. Okay, now we are a little lucky here because we only have two vectors and we only needed two vectors, and so we could use this not multiples of each other thing. What would have happened though if our differential equation had a higher order where we needed to come up with more than just two basis vectors? It does beg the question, how do we test for Li in this context where we're working with calculus? Because we haven't talked about that. So I want to take just a quick minute and explain that part. And we'll get this down in the notes, and this is a pretty quick thing. So given n solutions, let's say these are y1, y2, and dot, dot, dot up to yn of a differential equation, how can we tell if those set of solutions, so the set of y1 and y2 and dot, dot, dot up to yn, how can we tell if that set of vectors will be Li? This is a good question. How can we tell if those vectors will be Li? So again, if n is only 2, we can use the scalar multiples reasoning. But for more than two vectors, that doesn't work, as we've talked about before, and we've got to come up with something else. And so there is a new tool. Actually, this tool is mentioned in chapter 4 in the book. I chose not to bring it up at that time because we weren't working so much with calculus functions back in chapter 4. So you might have seen this in passing in the book a few chapters ago if you were really looking closely, but it's okay if you didn't, because I'm going to tell you right now. It is something that is named after a mathematician named Wronskian. So this is a so-called Wronskian, and I'm going to tell you what this is. We're going to form this matrix. I think I lied to you last week. I said chapter 8 doesn't have any matrices in it. There's one matrix. It's just this one right here. It's not so bad. And the way this works is you're going to take the Wronskian of W1, W2, and so on up to Wn, like that. And it turns out that this thing is just a determinant. It is a determinant. Give yourself a fair bit of big space to write out what's in this matrix, because it's a little bit long-winded to write it down. It's going to be an n by n matrix. And the way you fill it out is you just put your functions on the first row. So if you're wondering, yes, this is not a matrix of numbers. This is a matrix of functions. So inside the entries of this matrix, you're going to have functions. And what you do is you work your way down the matrix now, simply taking derivatives as you go. So on the second row, you will take the derivative of everything from the first row. So you have y1 prime, y2 prime, y3 prime, and so on. And then on the next row, you'll take the second derivative of everything. So you just keep taking derivatives. Most of the time, we're only gonna be looking at 2x2s or 3x3s. But the question does become, well, how long do you go? How long do you keep doing this? The answer is, well, you just simply go far enough that it becomes a square size. So you'll know when to stop, because you can't take the determinant of something unless it's a square size. And it turns out that what that'll end up being is n-1 derivatives of everything. So going across this bottom row, you'll have n-1 derivatives of all of those functions. Okay, so that's how you write down what the Wronskian is. But then I want to give you the theorem. And this theorem is called, sometimes you'll hear me call it the W test. It's the test for linear independence using this Wronskian, and it's very simple. It's very simple. What it says, guys, is if there is a value of x, let's give that value a specificity. Let's call it x naught. So if there is a value of x, let's say it's x naught, such that, sorry to be writing so far down on my board here, but I'm going to take the Wronskian of y1, y2, and dot, dot, dot up to yn of x naught not equal to 0. So such that that Wronskian is not equal to 0, then my set x1, my set y1, y2, and dot, dot, dot up to yn is Li. Okay, so this is a test for Li. This is a test for Li. If the Wronskian, now remember, the Wronskian is this determinant. This is a matrix of functions. So inside of this matrix, you have x's everywhere, right? So x's could be floating around all over this matrix, functions of x, I should say. But if you can plug a number in, a specific value, a specific number in for that x everywhere in the matrix and make that determinant not 0, well, that just means the matrix is invertible. That's a good thing. It's going to tell us that our functions are Li. The proof of this test, I'm not going to do it here. The proof is in group work number 12. So I am hoping maybe we can get to that on Thursday. So I won't go through the proof of it right now, but the point being that, yeah, it's a little bit more of a theoretical thing. So for today, I think I'll just leave it at this. Okay. So that is the test for Li. If you have a linearly independent set of n functions, right, you can use them to make a basis. And then from that basis, you can write down the general solution to your differential equation. So that's it. That's basically it. Okay, so I'm gonna save, I don't want to get sidetracked on the Wronskian too much right now. I'm gonna save that. Maybe I'll do an example of the Wronskian on Thursday as well. I instead want to give you, with the time we have here, I want to give you a recipe for how to come up with the solutions to certain types of differential equations, including the ones that are over here. So this is actually in the next section. So I'm going to kind of preview it here. What we're going to do here, guys, okay, so why is there still more to the story? What's the issue? The issue is that if Omar had not been here, we might still be trying to figure this out. Like, he happened to notice it. cosine and sine works, right? What are we supposed to do if we don't just eyeball it and guess the answer, right? I happen to think of two functions whose second derivative will cancel out the original function, right? But obviously, we don't want to be stuck with that approach for every kind of problem, because the differential equations are not all going to be quite this nice. This is too nice, right? So I am going to show you right now how to deal with any nth order linear homogeneous. This is the longest header of the entire book. I remember my publisher was like freaking out. I don't know if this will fit. And then the next word is constant coefficient. Differential equations. All right, so if we have that kind of differential equation, guys, by Thursday, everybody in this room will be able to solve any differential equation that looks like that. Let me just write down what it would look like. It's gonna be, a naught d to the n plus a1 d to the n minus 1 and dot, dot, dot plus a n of y equals 0. This is what we're looking at. And in this setup, all of those a sub i's are constants. They're just numbers. Right? And so the question is, how do you solve this? How are we going to solve? So actually, this would qualify for that. This is a second order linear homogeneous constant coefficients differential equation. This one we could just kind of guess the answer, which is what we did. But how can we do it for any differential equation like this? Like, what's the method to solving this? Turns out that the method, after years and years of working on a PhD and trying to get myself knowledgeable about how to solve math problems and flex my muscles about all this brilliant ideas of math that I have, turns out that the method for solving this differential equation is to guess the answer. So glad I went to school for 10 years. So we're going to quote unquote guess the answer. It turns out that there is a good guess. Now, I wasn't even smart enough to figure out what the right guess should be, but it turns out that the right guess is the following. Y of x equals e to the rx. All right. Now, that's the right guess for this kind of differential equation. One of the common mistakes I see is that I might give somebody a differential equation that does not have constant coefficients. And then it turns out this is not the right guess. But for this kind of differential equation, such as, let's just keep, this is from the homework. We're going to do this problem in just a second. This is number 24 from tonight's homework. It's asking you to solve this. This is a second order homogeneous linear constant coefficient differential equation. And they even tell you in the book, find two linearly independent solutions of the form e to the rx. Well, once you write down a guess, guys, then what you're going to do with that guess is you're going to plug it in and see if you can solve for r. Right? So I'm going to do that here. I'm going to take a naught d to the n plus a1 d to the n minus 1 and dot, 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 an times e to the rx, set that equal to 0. Now, do we all know how to take derivatives of e to the rx over and over and over again? Because that's what we're going to have to do. Every time we have a d being applied to e to the rx, that means take the derivative. The derivative of e to the rx is r e to the rx, right? You pull the r down in front. So take a look here, guys. On this left side, a naught, this is n derivatives of e to the rx. That means this r pulls down n times. Oh, sorry. Yeah, so, well, I'll just leave the e to the rx over here. I'm gonna factor out that e to the rx. The next term is just n minus one derivatives, which means I will pull n minus one powers of r out. And essentially what happens here, guys, is that all of the d's just turn into r's. So on this homework problem here, because I don't want to neglect this problem, this is just d squared plus 7d plus 10 of y equals 0. So you can just kind of put this as an example on the side. If we just try to put in y equals e to the rx, what will happen when you put in that guess is all of the d's will turn into r's. By the way, is e to the rx ever equal to 0? This exponential function here. If you think about e to the x or e to the 2x or e to the 3x, the graph looks like something like that, doesn't it? That's your exponential function. Is it ever crossing the x-axis? Not at all, right? Cancel it. Cancel it. That's not going to be 0. So what that tells you is that this part has to be 0. And this part here is obtained by just simply changing the d's to r's. You don't even have to think. You just change the d's to r's, and this, by the way, has a name. It's called the auxiliary equation. And you just change the d's to r's. And you just have to solve for r now. So on this problem here, number 24, let's just finish this off. There's your quadratic equation. Does this factor? This should factor nicely. This is just what, r plus 5 times r plus 2 equals 0. So r is -5 and -2. Says, so what are my solutions? Just finish this up real quick. The two solutions are going to be e to the -5x and e to the -2x. Again, since I could use my Wronskian now, which if I had another 5 minutes, I would. But I'm not going to use the Wronskian to point out that these are Li. I'm just going to say one more time that they're not scalar multiples of each other. And so these are Li. And so then finally, my general solution is C1 e to the -5x plus C2 e to the -2x. That's your general solution. Are there any questions about it? Isn't that easy?
Yeah.
You know what? Friday's entire homework assignment is basically this. There are a couple of issues though. One issue, and we can't talk about them tonight, but one issue is the roots of this auxiliary equation. Just like with the characteristic equation with the lambdas, it could be complex numbers or they could be repeats. So on Thursday, I'll explain how do you deal with repeats or complex numbers for this auxiliary equation. One last comment. I know you guys are ready to go. Real quick, on 35, I just want to point out 35 is not like this. Because on 35, the differential equation, I won't do the whole problem, but I just want to point out, the differential equation is not constant coefficients. You see these x's here? Those are not constants. So you cannot use this guess to do 35. But they tell you what guess will work. They tell you on 35 to use x to the R. So what you need to do is take two derivatives of this. Please take this derivative carefully. Use the power rule. Take the derivative carefully, plug it in, factor it out, and do the same kind of algebra that we did here and solve for what would be two values of R again. So on this problem, you'll also have two values of R, but it's not coming from the same auxiliary equation. All right, guys, sorry to keep you a little bit extra, but thank you for your time today. And I will see you when I see you. Office hours later tonight or else on Thursday. Bye for now.